Hello everyone, my name is Mohamed Moustafa. I'm an associate professor at the University of Nevada, Reno, and I would like to provide you today in this short video an overview of a recently completed project for the ABC UTC. The title of the project is the application of methacrylate polymers, or in short, polymer concrete for seismic ABC connections. I had two graduate students who worked on this project and their work is acknowledged. So for ABC, like the focus is on connections in this project, and we have two types of ABC connections in general, or in terms of the application, non-seismic application, which you see here on the left-hand side, like the bridge deck panels, and seismic applications, which was recently introduced in one of the pilot projects in California, as you can see here on the right-hand side. So for this project, the focus is on seismic connection. Most of these connections have traditionally, or not traditionally, I mean in the last decade or so, when they start getting popular in the US, they have been using ultra-high performance concrete, or UHPC, to simplify reinforcement, use smaller joints, and have better interface bond, and so on. So if you focus on seismic connection specifically, we have two popular options like pocket connections, or sometimes we call them socket connections. It depends how the column is plugged into the footing or the cap beam, and also the grouted ducts connection. And the one that you saw in the picture, which I'm showing here again, is the one that have been implemented in California, the grouted ducts connection, and they have used ultra-high performance concrete in California based on some work that was done here at the University of Nevada, Reno in the few years ago. So this could be used for both column to cap beam connection and column to bent cap connection and column to footing connection as well. So as I said, UHPC has been traditionally used for these type of connections, and UHPC works great. But what is the challenges here? We have mixing and curing process complexity. Many of the contractors wouldn't like to use UHPC. Sometimes the material is not available, especially in the West Coast, for example. Some of the non-proprietary mixes are emerging, but they are not robust enough to expand at larger application. So we thought of some alternatives that can eliminate the sole sourcing, for example, for some of the UHPC vendors, and we thought about the methacrylate polymer concrete. So the motivation for this, we have already used polymer concrete in the non-seismic connection in one of the earlier ABC UTC projects as well. And you can see, or we showed actually that this works perfectly fine for decks. So this motivated us to use it further for ABC. The nature of the polymer concrete is that it comes in two components. For example, that's a commercial project from our industry partner. You see the dry mix and the liquid, you put them, and in less than 5 minutes, you can have a mix, and you get very good properties that are almost similar to UHPC with 2% steel fiber in terms of the connection. So polymer concrete is an uncementitious material that uses organic polymer like the methacrylate instead of Portland cement to bind both coarse and fine aggregates. So it can be used for both. It can get to the strengths almost in 24 hours, and this is all what we need for ABC applications, for instance. So the research objectives is to extend the use of polymer concrete to this specific, seismic connection, the grouted ducts connection, characterize the material and mechanical properties of polymer concrete, and conduct a large-scale column test to show that the material work at a meaningful scale and in meaningful application. So this slide just shows some of the basic mechanical properties of polymer concrete. The full details, of course, are included in the report. We did a lot of material sampling to test prisms in flexure, cylinders in compression, even cubes in compression as well. We did some dog bones to do some tension, and we did both with and without aggregate so that we can get a sense of the material. Then we moved on to the next stage, which is the large-scale column test. We used some of the previous work that was done here at UNR that used UHPC, some of the work that was done by Tazarf and Saidi, and some of the work that we did for Caltrans a few years ago using non-proprietary UHPC. So same research team, we did this for Caltrans. So we used some of these columns so that we can compare, as you'll see later in the last slide, the reinforcement details and the dimensions of the specimen is, as you can see here, and the construction. Usually you like to mimic precast construction, so we constructed the footing separate from the column, and then we did the polymer concrete. We filled the duct with the polymer concrete, and then we plugged the column inside the footing, and here is the assembly of the specimen. The test was tested inside the earthquake engineering lab at UNR under combined axial and bending loading. Static test, as you can see here, that's a test setup. This is the loading protocol that we used, similar to the loading protocol we have used in some of the HPC columns so that we can compare. And here are some sample results that you see. The main thing here is the damage that we have seen. All the damage that we have seen is in the column. Nothing happened in the footing or the ducts, so the polymer concrete worked perfectly fine in the connection. The column was able to develop a full plastic hinge, as you can see from the visual damage here after the test was concluded. But more importantly, this is the behavior also as we capture the force-derived relationship. And you see this hysteretic behavior is a good sign for good energy dissipation as required by the current, like a ductile-based design. When we did the envelope from the two sides and we averaged them, we get the average pushover curve, and you can see here we meet the ash to allowable ductility demand for this type of connection. So we are like this type of column. So we are definitely, satisfying the design requirements that we need. We compared, as I said, with several previous columns from the old projects, and here this is just a sample comparison with one of the similar identical columns that used non-proprietary UHPC. As you see here, alternative A. R1 and versus the polymer concrete in alternative 2, and they were very comparable, same dimensions, same column design, and the failure load in the polymer concrete was even slightly higher. So this also shows us that we can mimic or what we can get what typical proprietary and non-proprietary HPC would do. We looked at local behavior as well, strain in the reinforcement and the curvature profile, just to make sure that the plastic hinge we see visually is confirmed using local and global behavior as well. So as I said, this is meant to be only an overview video, and the full details will be in the final report that will be posted on the project website. So for just some concluding remarks, the observed mode of failure is the full plastic hinge in the column, which is desired from the current design codes. The PC or the polymer concrete fill ducts, the column was able to go large inelastic deformation with drift capacity almost 10% or more, which compares very nicely to cast in place, conventional, construction or column with commercial UHPC or even columns with non-proprietary UHPC. All of them were ranging between 9 and 10.5% drift capacity. So we were all in the same range. So this confirms that polymer concrete work almost as well as UHPC. The major displacement ductility was at least 7, which exceeds the ash requirement. For a single column bent, it's 5. For double column bends, it's 6. So the 7 exceeds both anyways, although only the 5 will be applicable in this case. So overall, the polymer concrete fill duct connection are recommended as a suitable precast column to footing connection, as well as column to cap beam. There's both moment connections for both moderate and high seismic regions because of the drift capacity and the full plastic hinge that you have seen here, and we would recommend it for future implementation. So thanks for watching this video, and if you have any questions about this project, you feel free to check the final report and also email me if you have any questions. Thank you.